So welcome everyone at session 12, sorry, which is about deep reinforcement learning. So we have two parts here. So as we see, we have deep learning, which is we already know, and we have the reinforcement learning, which is basically something not that new. It has been used in artificial intelligence for a long time ago. It's used mainly to train robots, or agents they called. It was used to play games, and also now it's one of its main use cases basically to play games using AI. It's used, for example, to now to beat humans in chess and also in Alpha or Go games, which are very complicated games. And the idea of deep reinforcement learning is basically to combine both worlds, the deep learning, or actually the deep neural networks, with reinforcement learning together. So reinforcement learning is a type of machine learning that is unsupervised learning, which means there is no labeled data needed for reinforcement learning. The machine here also doesn't rely on data, so it's not a clustering, for example, or it's not an autoencoder. That is also unsupervised learning, but it needs data. Reinforcement learning relies on experience, so which means the difference here, we don't need to prepare data for the agent. What we just needed to prepare the environment, and then we put this agent in the environment, then the agent would learn from the experience by just try and error, then it will learn how to perform. So basically the experience is gained through an interaction between the machine, which is the RL here, and the environment. Like for example, the environment is like the chess environment or the checkerboard environments. So the game environment itself. And the role of the agent is to do some actions like move, hit, for example, carry, or move left, move right, so on. And when the agent moves, of course, it would affect the environment. It would change the environment, like it would throw a ball, for example, then the environment would change with these actions. Then the environment or the engine would send basically a reward. And this reward could be positive or negative reward. For example, positive if the agent does a good action that would lead, for example, to win the game, if we're talking about the games. Or if we talk about robotic, for example, that the agent could pick up, for example, a cup, and so on. So basically, this is the reward, also an important part of the reinforcement learning. If you are familiar with game theory, which is mainly many of the theories in game theory are used in reinforcement learning. It's like the reward is like the utility of actions or of choices. So the goal of the reinforcement learning is always to maximize the reward at the end of the game. So I want to win the game, or I want to win the task that this robot is trying to do by maximizing the reward, and which basically represent winning the game. So the idea in reinforcement learning is that we have the agent, which is the AI agent, which is here the machine learning or deep learning model. If you are talking about deep reinforcement learning, the agent does an action, AT, that changes something in the environment. Then the environment would send the next state, because the environment has a current state, and the next state, we'll see what the meaning of that later. Then it gets the reward and the current state, and also does another action, and this basically loops. And the agent would start to learn in order to maximize the reward, okay, and avoid negative rewards, for example. Let's take a motivational example to understand what is reward, what is state, and what the actions are. Let's say that we are trying to train an AI agent to play ping pong with, for example, which has two parts or two players. The first one is our AI reinforcement learning player. The second one is a built-in player, which is used some rule-based, for example. And the difference is, for example, this knows the game by rules created by humans. This will try to figure out the game by using reinforcement learning. So this one is the artificial intelligence here, because this one actually learned the game by itself. This one is built-in player. So we have the environment, which is the ping pong game. We have here the first our player, which is the AI player. This is the PC player. This is the ball, which is basically important, of course, for the state. So, for example, what is important here to understand is the state of the game. So I talked about the state here. So what is important in the state of this game is the position of the ball, of course, the current state, the position of the PC player, and the position of our player. So this is basically the current state. Now, when it comes to deep reinforcement learning, the basically the advantage there is like it's like humans. Our state would be the input image of the game. So deep reinforcement learning mainly use images as an input. It's like humans looking at the game and playing the game. The idea here is basically that an AI agent would look at the game and play it. And basically the input state would be the input image. That, of course, within the input image, we also, of course, have the position of the first player, second player, and the ball. Not the player has different actions to do. Is either move up, move down, or stay still. So don't move up or don't move down. The reward that this player could get is basically +1 if we score, which means, for example, this ball basically will go here. That means +1 as a reward for our player. -1 if they're letting the ball in, and 0 if nothing. If it is not scoring or letting go. For example, if the ball is still in between these two players and they are playing, and it's not scoring or letting in, then the reward will stay 0. The way you design the reward function, of course, is very important in reinforcement learning. For example, another one would say, I want to, whenever this player could reverse the ball, which means could hit it back, then I also want to add a reward for that if it's important. For example, in this case, as I said, which is scoring is reward equal to 1. In this case, when you let the ball in, it's -1. If the ball somewhere in the middle, it is equal to 0, or even here, for example, it's equal to 0. As I said, other designer would say, no, I want to also add the rewards for that move, and basically it would be equal to 0, or equal, for example, to +2, for example, for that. So in our game here, just basically is also, if in this case it's also reward 0. So if it's not scoring or letting basically the ball in, then it's equal to 0. So what is the experience here that we need to store basically, or need to learn from? In reinforcement learning, we need to store, actually, to memorize a state, for example, which is now this is a current state. The action that is basically taken or decided by the reinforcement learning agent, which is here, for example, moving down, and the next state, for example, when the agent decided to go down, then the next state is basically that the agent is down and it hit back the ball. So we have here state, action, next state, and the current reward. And the current reward here is equal to 0 unless you have another reward function. For example, you put here +2. But now what you need to understand that we need to have these 4 parameters in our experience at every moment or every second of the game. So we have the state, action that is taking the next state. And this what we meant that when the agent makes an action, it changes the environment, of course, because when it moves down, it's basically changed the environment. And basically this is the next state and the reward. Or, for example, the agent decided to go up, and here move up, then the next step is equal to st1, and this actually should be -1. I just will correct it now. Because we let the ball in, so it's basically now this would be the reward of my or of the agent action to move up. So the game experience in general basically is a long memory along matrix, let's say, that in each row we have basically this for, or combination of this for, which is the current state, the current action that is taking, the reward that we get, and the next state. And we will do that for different, basically, along the game. And sometimes the next state would be terminate, where when the agent lose the game, for example. And sometimes it's used in order to improve also the performance of the model. So there are now taxonomies, or actually terminologies in RLL. There's what is called the policy and value function. So the policy basically is a decision-making function that takes a state and decides what action to take, and this is called a policy. So an input is an action, is a state, and the output is an action. Okay. The value function it's also called the utility function, is taking the current state is an estimation of the value, mainly the future value of the current state that we are in. For example, if I look here and I know that the agent is going down, then the future expected state, actually you can see it. Yeah, I'll talk about it later. Let's talk about now the policies. So there are good policies and bad policies, of course, and the agent needs to learn good policies always. And basically, the policy, as I said, it takes the state and predict the good action or the good policy, which means the input state, and predicts, for example, here going down. And this is a good policy because it will lead to hit the ball back and maybe score. And this is basically when it learns a good policy. Bad policy, for example, when it decides to go up here, and then it will let the ball in and it will get negative reward. Now, bad policy leads to bad value function, because if I basically move up with the current state, I would let the ball in. And this basically, if we are considering in the value function the action and the state, then the output of the value function would be equal to -1. Or if I hit the ball here, basically the value of that would be, for example, if I look at this state, then the value function would tell me it's a 0, or actually it would tell me it's equal to 1, because the value usually consider not only the current reward but also consider the future reward. What the meaning of that? When the agent looks at here or at here, and it knows that from its good policy it will move down, then it will basically predict that the value is equal to 1 of this state. Why? Because it knows that if it hit the ball back from here, this is a good move, for example, where the ball would actually just fly in this direction, and maybe it knows that the other player would not have the time to reach it. And for example, after future states, because here as I said, every move, every millisecond is a new state probably, then for example, when it's t plus 15, when it score, it would get at the end positive or +1 reward. So the value of moving down and st, or the value of st itself, and knowing that this agent has a policy of moving down when it sees this st, is equal to the current reward plus the next reward plus the next reward, which is basically, because everything in between is equal to 0, so it will be 0, 0, 0, 0 plus the 1 at the end. So actually, from this step here, if we have a good value function, from this step here to tell me, okay, I know that now you would get at the end value of equal 1. Okay. And the idea of value function, it could be very good in order also to predict that at the end of the game you would actually win this game, even if you are looking, for example, at your historical score and you're looking at the moves that you're doing, then the value of this game is to you that because you are winning the game. So what is the model? We have seen now the policy and the value. What is the RL model? It's actually the model of the environment. So it's not the neural network model. It could be neural network model, but it is not the agent model. I mean, it is the agent view of the environment. So It maps the state action pairs to probability distribution over states. The idea of models basically is that taking the current state, predicting the next state. Okay, so it's basically doesn't care about the actions here or reward. The model here basically is taking an input state and predict the next state. And we need the model in RLL if we can't do that prediction, or if actually we don't have control of the environment. Like if, for example, when it comes to games, maybe model is not always important because we have control of the environment and we probably can predict easily what is next. But when it's come to real world, basically examples, for example, we let's say I want to train our neural network with reinforcement learning to drive a self-driving car, then I need to have a model that has a simulation or actually understand how the state changes in the real environment, because I cannot try or I cannot put an agent in real life and let it do accident and get negative rewards, for example. So the idea of the model is a simulation of the environment, where it simulates how the states could transit, for example, from one state to the other state. Okay, so it's mainly to predict the future state from using current state, but of course it could predict the values, also all that. This is the idea of the model in reinforcement learning, and this is why you would hear two different basically types of reinforcement learning. We have the model-based and versus model-free reinforcement learning. The idea of the model-based reinforcement learning, it requires a model. That means that we need to have a model, we need to predict the next steps in order to train our AI agent. Model-free, we don't care about the model of the environment. We don't care about the prediction of the next states. We only observe the current state, and we basically the current and only the next state, for example, and then we need the reward, the actions in order to train the network. When it's model based, like in AlphaGo, for example, or AlphaZero, which is an AI that's play Go game, it's model based because it needs to predict long term in the future what are the future states that can happen starting from the current state. So this is basically why it needs the model. If I don't want to predict all these future states, then I don't need the model based, I need model free. If I only care about the current state and only the next state, okay, which comes after my current action, then it is basically model free RL. And under model based and model free, there are different techniques to do reinforcement learning. So we cannot cover all of them because they are actually, you need one complete course for reinforcement learning. I'm covering here the most important one, which is the Q learning, and basically deep Q learning mainly, which is model free. But actually, you will see they all rely on actions and reward and state and so on. So if you understand this, you have the basic to understand the rest. So this, as I said, I want to talk about Q learning, which is a model-free RL. And then I will talk about the deep Q learning, which is a Q learning over deep neural network. So what is Q learning? Q learning is learning the action value, which is called the Q matrix. So the Q matrix basically is a matrix, let's say it has rows and columns. And the rows, we have the states, for example. And by saying that, when it's come to matrix, that means we have a finite number of states. Let's say I have a different state, 5 different states. That means this Q matrix has 5 rows, for example. And the columns are the actions. For example, if I have a state 0, then I have different possible actions. And at each cell now of this Q matrix, we have the value of actions at certain state. Let's say I'm a state 0, then I have 5 actions. Action number 5 equal 100, which means the value of that action is equal to 100. So it's like a value function, this Q matrix. It represents how good to take an action at a particular state, basically a scalar value that is signed over an action, a given state. So we have the row, which select at which state we are. Then we have the basically the columns, which tell me which is the best action to take, and the best action basically has the highest value. This is what would be selected. So during the learning, Q matrix basically is updated using the Bellman equation. So we will see what the meaning of that in example later, but the idea is that the Q matrix started as a 0 always, everywhere. So for example, for every state, we don't know what is the value of all the actions. So the Q matrix starts as a 0 matrix. Then we need to update this matrix by doing now some experience. So the agent will start to play with the environment, then update its states, and then update the matrix. So first of all, what is important to understand here that first we have the old value that start at 0. We need to update this old value by adding some new values that are coming from experience. We have the learning rate here, which is coming from, we understand from the gradient descent as well. It's the same idea here, multiplied by the reward that we get from the action, plus discount factor from the future basically states. Don't worry about that now. I'll explain to you an example what the meaning of or what is happening here. Let's take this example. Suppose we have this is our game. We have 5 rooms in a building connected by doors as shown in this figure here. So we have 5, basically we have 0, 1, we have 5 rooms and we have the outdoor. And we will number this room from 0 to 4 basically, and the outside would be, which is a big room, or the outside yard here would be equal to 5. So here we see basically the connections. So to see basically that we can go to state 5, which is the outside, for example, from room number 1, or state here also. So the states here are also the rooms. From room number 1 or room number 4, we can go to 5. We can go to the outside. This represents the connections. For example, I can go also from 5 to 1 and also from 1 to 5, and I can stay outside. Basically, if I am at 4, I can go to 5 or go back to 4, from 5 to 4, but I cannot stay. So except the output state. So this is basically the game frame that we have here. Only if you are in the output, you can stay there. But if you are in other rooms, you have to move. For example, from 4, you can go to 3. And these connections here, basically, they are representing the doors between these rooms. Now let's talk about the reward function, or how we are rewarding these moves. Remember that the goal of this game, that wherever I start as an AI agent, I need to go out. So if I start at 0, then if smart AI agent would go to 4, then go out. For example, if it is a less smarter, for example, it will go from 4, then it go to 3, then go to 1, then go 5. It basically, which means it takes longer to go to the output. Then 2, for example, it go to 3, then 1 to 5, or 3, or basically 3 to 4 to 5. So this is basically the goal of the game. This is what the AI agent need to learn. And this is suggested reward function for this game. It's, as I said, the reward here is designed by the one who is basically training that AI agent. So it could be, you could have different designs for the reward, but here's the idea that, like in the ping pong, whenever we basically moving between these rooms, whenever the ball there in between, then we don't put any action, so, or any reward, so it's 0, 0, always 0. But when we go from room number 1 to room number 5, it will be 100. And if we stay at 5, so whenever we are at 5 and we stay at 5, because we need to stay there, it's also 100. Or if we go from 4 to 5, it will be equal to 100. So, and here is the key basically value of the Q learning and the Bellman equation, because if I am room number 2 and I'm getting reward 0 when I go to number 3, how the agent would understand or would learn that this movement here has a future value of 100, because If I move to 3, I'll get 0 reward. And if I go from 3 to 4, I'm getting also 0 reward. But if I go from 4 to 5, now I get 100 reward. So from this part, the agent should understand if that this path at the end would get 100 reward. This is a future reward. And this is basically the idea of the Bellman equation that we have, that we are connecting current reward with the future reward. And the discount connections that we have, the factor basically that we have seen here, is the idea of it, how basically how much we need to include the future in our current decision. If it's equal to 1, that means we need completely to consider the future in our decision. If it's equal to 0, that means we are only relying on the current reward in our decision. Okay, which if we do here, for example, it's equal to 0, then the agent would not learn anything here, as we will see now in the example. But let's now consider now these reward functions. So this is just here the description of these reward functions. Now, if we put that reward function in a, like here in a matrix, where -1 means it's not an allowed move, because I cannot go between room 0 and 0. I said we cannot stay there. I cannot go between 0 and 1 because there's no door. There's only door between 0 and 4, which has a value, reward value of 0. And here, for example, from 1 to 5 has a value of 100. So these the zeros here are the reward functions, and 100 also. And -1 means it's not an allowed or unallowed move. This called them reward metrics, but what is important for us is the Q matrix, as I said. The Q matrix has a number of rows which equal to the number of states, and number of actions, which basically, or the number of columns, which equal to the number of actions. Now here in this game only, not only, but this basically could be in other games, but in this game we have the number of rewards, or the number of actions is equal to the number of states. Because if we are at state 0 and we decide to 0, that means we are going, or we are staying at room 0. So the action here means to which state I'm moving from the current state. So what we see here in the rows is the current state. For example, if I am at this row, that means I'm in room number 2. And if I decided to 4, for example, as an action, that means I need to go to the room number 4. As I said, in the basically the Q learning algorithm, at the beginning we start with 0 matrix. So the Q matrix is 0 now. We don't prefer any reward for any action from the other. And we need to learn this matrix. So there's just here a summary of the Bellman equation, that the Q state action, the current state and the action that we are taking, is equal to the current reward that we get, multiplied by here our discount factor, which sum by the discount factor multiplied by the maximum possible future value that we get, which means here max from the next state that we decided, and all actions. So the meaning of that, we are taking the Q value of the maximum action that we could take from the next state. And this way, the way we are connecting the current state with the next state, because the next state would connect it with the next state after that using the same equation. And this is how we connect basically the current, as you will see now in the example, the current reward with the future reward, because the current reward equals 0, but if we connect it using this Bellman equation, it will be equal to 100 at the end. So here, if you just want to read, but I will explain what is happening here actually. So let's assume that gamma equals 0.8. That means we are considering 8% of the future, let's say. And let's say that we are at the second row here, which means we are at the state 1. That means we started the game with the room number 1. So we are starting the game here. So there are two possible actions to take with respect to the rooms. If I am here, is either to because there are no other doors with the other room, so they either to go to 3 or to go to 5. Now the agent is taking its action from the Q matrix, just remember. So it doesn't know yet what is the values of taking 3 or taking 5 directly. When it doesn't know at the beginning, because here it doesn't know basically what action gives me the maximum reward, then at the beginning it will select randomly. Okay, so let's say that with randomly it's selected to go directly to number 5 or to the room number 5. Again, we are here and we can only go to 3 or 5, and randomly it's selected to go to 5. Now, because it has done that, basically it will get, for example, a reward of 100. So if we look here at the formula, we have state action, gamma, max, and so on. We are at the row number 5, row number 1, which means we are actually here. We are at this first room. We decided to take 5 as our action. So this is equal to the reward that I would get from moving from 1 to 5 plus 0.8 multiplied by the maximum of the next state plus all actions, which is a max between 5, 1, 4, 5, and here 5, 5. So because if I am at 5, I can either stay at 5, which is here, or move to 4, move back to 4, or move back to 1. Now, because the matrix at the beginning still has no values inside, then what I get here only is the current reward, which is equal to 100. And what I get basically here is that it would be 0 plus 0.8. Now let's say at the next state, so this episode is finished because we went out. The next state we start at state number 3. Instead of randomly we start at number 3, or which means we started with room number 3 instead of room number 1. So I will show you just how to do the calculation. So we started at room number 3. That means we are at room number 3. Because now at 3 at the beginning is zeros, so don't consider here the 80. This will be the output of our calculation now. You will also need to randomly select where to go. And from 3 we can go the 1, for example. And let's say that the agent randomly selected to go to room number 1. The current reward, the actual reward that we would get from that is equal to 0. And now the 0.8 multiplied by the max, let's say the max possible, or the max Q value of the next state. So basically here we are taking the max of Q5 and all the possible Q values. If we look here, for example, sorry, is 1 because we moved to room number 1. So we are at 3. We randomly select here 0, or select the action number 1, and the value here is 0. Then from 1, so that means we are here, we move to 1, and that means we are now at row number 1. And if we are here, what is the maximum possible value that we can get at room number 1 is equal to 100. So basically, that means what we have here is 0 plus 0.8 multiplied by 100, which would be equal to 80. And that's why we see now here 80. And this is why how we connected the decision of moving from 3 to 1 with the future reward. Because now when I want to move from 3 to 1, I know that I would get eventually an 80 reward of that moves. If, for example, this origami equal to 1, then it will be 100 here again. because the agent would know if I go from 3 to 1, I can then go from 1 to 5 and get out. This is how we can connect the current reward with the future reward using the Bellman equation, okay? So if we continue basically doing that, which means we are starting from random positions and moving from one room to the other room, then just updating the metrics using Bellman equation, which means we observe the current reward, then we look at the next state that we moved to, and we take the maximum Q value of that next state, and we update now using Bellman equation. We would end up with kind of experience or Q metrics like this, which would have here basically could be high values because we are always adding them. So what we could do now, we do normalization, which means we divide it by the highest value. And we end up with this Q metrics, which basically represent the knowledge of now of this agent. What knowledge, for example? The idea here that this agent would, if started now at room number 3, it would look at the maximum 3 possible moves are 80, 51, and 80. So it understands if it moves from room number 3 to 1, and then it would get a reward of 80. If it moves from 3 to number 2, it would get to the outside, but it would take longer. That's why it gets 51 here. If it's, for example, from 3 to 4, it gets also 80. So in this case, it would decide basically, it should pick the action that brings the maximum value. So it's either 3 or 1. It would randomly select either 3 or 1. Now, if the agent is in, for example, at 4, it will look here, it would see, for example, if I go directly from 4 to 5, for example, because I can directly get 100. If the agent starts at 0, then it would see that if it goes to 4, it would get at the end 80, for example. And this is basically the experience that would now, using this experience, the agent would always go to the outside very quickly because it knows what is the reward and what actions are to bring the highest reward for that agent. So this is the idea of the Q matrix or the Q learning. It's very simple, as I said, using the Bellman equation. Now, why we need deep Q learning? What we have seen now, a problem or a game with a finite states, which means we had 6 states representing basically 5 rooms plus outside. When it comes to infinite states, infinite number of states, then we cannot do matrices, right? Because it would be very large matrix and we cannot do that anyway. For example, if we go back to the ping pong game, we said that the state represents the current position, the current image of the game, for example, and for example, this state is different from this state and from this state. So we have basically infinite number of states when we talk about images and time varying images. Like the state of the environment around you now, that can change with any movement. It's an infinite number of states. And when it comes to that, we cannot do matrices. And what we do actually here in deep Q learning, we try to build the idea. So what is the solution? The solution is to reduce the dimensionality of the game state. So to reduce the dimensionality of the input scene, input image, and build a representation of that states using, of course, neural network. Then using this new network, while we're building this representation, while reduce dimensionality from high input state, which is basically the input image, then we basically do dimension reduction using feature selection and high-level features, as we have seen in the convolutional neural network. Then at the end, we can use this network to predict the Q value of each state. So the idea here, it's like, let's assume this Q is our matrix. Then it takes, it's our matrix and it's our neural network. Then let's see the value 0 as an input. This very simple neural network. When it sees an input, the current state, which equals 0, then it will predict that if you move to 0, it will be 0. If you move to 1, it will be 1. It will be 0, sorry. If you move to 2, it will be 0. If you move to 3, it will be 0. If you move to 4, it will be 80. And if you move to 5, it will be 0. So the network, the neural network idea here is that will basically copy this Q matrix. It will approximate, as we said that neural network is a function approximation. So it has an input state, and the output is the value of the action that you can gain at the end of, for example, the game with respect to each action. So this is the solution that we build neural network. Mainly here it's a convolutional network because we are looking at the game scene. We do convolutions, then we predict the value of each action that we can take. Okay, so we have the state, which is the input scene. We have a network. Then this network would give me the value of each action that we can take. Now, this sounds good, but how to train this network? It basically will rely on the Bellman equation, but the idea is how we can build the cost function of the neural network, because we need the cost function to do backpropagation and to estimate the gradient of backpropagation. So what is the cost function for this neural network? Looking back at the Bellman equation, where we have the QT, or actually the Q current state and current action, is equal to the reward that we get directly plus the discount here factor multiplied by the maximum Q values of the future state. So this is the Bellman equation. Let's say that if we move the right side here to the left side, and which basically that means should equal 0. Now we can build the cost function, and the idea of the cost function, so if the left part is exactly at the right part, that means the Q matrix is perfect. That means basically here is equal to 0, which means there is no update is needed anymore. And this is our cost function for the neural network. The difference here when it comes to deep Q learning, you would see that it's basically the Q is basically representing a neural network here. It's not a matrix. It's parameterized by, of course, the weights of that network. And this neural network basically takes a state and predicts the actions or the values of these actions. And the idea here is that this is our cost, for example, at time t. So we have a state at time t, and say t equal to 5. Then we have the Q value with respect to that state and all the actions that are possible. These are predicted from the network. Then we have the reward. This is now something we get from the experience. This is not predicted from the network. This we learn from the experience. Plus again the discount function here would be sorry, this should be also okay. Because here the negative would be to all the part here. Okay, so basically now this is our cost function. This is the same network that would be used to predict the values of the next states. Okay, so all possible values of the next state. The goal is to always to minimize the cost in your network. And if we minimize the cost, that means our prediction of the Q value is always correct. And how to estimate if it's always correct? By just estimating the difference, the temporal difference is called, between our current prediction with the current state and the reward that we get plus the discount factor multiplied by the max, also the neural network using the next states here. That means when the cost function equals 0, that means that this network actually, or the network at this step, could correctly predict what would happen in the next state. So just to understand basically what is the architecture of this network, let's look again at the Q, basically the ping pong game. As I said, the input here is the image of that ping pong game, and we do then convolution, for example, polling, convolution, polling, then convolution, polling. Then we do flatten, for example, and then concatenating of the flattened vectors to have basically here fully connected network, like in the convolutional neural network, exactly the same. Then here we have three outputs representing the Q value of these three possible actions. If we look back at the Q matrix, as I said, here we have the states and here we have the actions. And when it comes to the ping pong, we have three actions only. So we have three columns if we have a Q matrix. And these three columns are basically represented by the three outputs here, up, down, and stay still. So let's say now we have this input here, and we have the neural network. Then we are predicting so the network is predicting the Q value, or the value of moving up, the value of moving down, the value of still. So it's telling the agent, if you now move down, you would get at the end a Q value equal to -1. If you go up, sorry, you get -1. Because if you go up, then you will let the ball in. So the network predicted from this state that if you go up, you would get -1. If you go down, you would hit the ball back and you might score. Then you get +1. And if you stay still, you would also let the goal in and it would be equal to 1. So what happens here that the agent look at the image, apply the network and get this output, then it will select the action that has a maximum value, so it will move down. And this basically represents the same what we have said here. So for example, why the agent learned that if it goes down it will equal 1, because we said that the current move is connected to the future reward that we get, which equal to 1, because if I move down, then I would hit the ball back and I might score. So basically this is how we connected the current reward with the future reward, because if I go down directly and I hit the ball, it will stay the reward equal to 0, as you remember, but in the future it will be 1. And this is like what we've done in the room game example. At the beginning we have, if you go from room number 3 to 1, and then the current reward is 0. But what you would know now, if you go from 3 1, you can go then from 1 to 5 and you get 100 at the end. This is basically how we connect that. So the cost function, for example, how the cost function is calculated. Let's say we have here the current state at time st. We apply the image of the current state on the convolution network and we get the Q values that the network think about the current state, for example. So the network tells me again, if you move up you get -1, if you move down you get 1, and if you stay still you get -1. Now we also apply, just remember always, we need to apply on the network the next state. Okay, so we always need to basically store these pairs of state and next state. Then we have the next state, which here basically if it's moved down. Then here we have also Q values of if I go up, again, I might get -1 at the end. If I stay still, for example, I would get +1. And if I move down, I get -1. Let's say basically these are now Q values for the next state. These are Q values of the current state. Now I can apply the cost function, because now I had the neural network using its current state and moving down into this one, minus the st, because it's the action that would be taken, of course, because this is the action that has a maximum value, minus the current reward that we could get is equal to 0, because as I said, the current reward would be 0 if it's not let in or not scoring. Plus, let's say that our gamma equal to 1 multiplied by the 1, because the maximum value that the network is actually predicting here, wherever it is equal to 1. Okay. Why is that? Because again, if we hit the ball and we are staying there, then we'd score. Okay. And for example, let's say that this agent was too fast and actually it could hit it back. Then if I stay still here, then I can hit it again. But if I moved up, for example, then I might lose this ball. This is why if you stay still there, it's equal +1. If it is you go down or up, you might get -1. But the idea here that now the network predicted that if from here, if I move down, I'm getting, the network said that you get +1. And if we connect this, what is the next prediction, it's also +1, then the cost would be equal to 0. And this is how we can connect the current with the future. And this is how we can calculate the costs of the network prediction. Let's say that the network prediction here was, I don't know, that you would get reward equal to -1, and here -2, and here -5. Then it would also select the down with -1. But here the cost would be higher because it's different from what the reward that you get in the future. So the network will start to train until it knows that whenever it sees a state, then it will predict what action would bring the highest reward in the future and would select that action. So how to because we need this cost function, we need to, for this to evaluate this cost function, we need always to have the st +1. We need to have the rewards, of course, and we need to know the action that is taking in order to estimate the cost function, and we evaluate the cost function, and after evaluate the cost function, evaluate the gradient of the cost function in order to update the weights. So we need the experience, and the experience, as we said before, is basically a matrix where here we have the important parameters, and then we have basically along the memory, so long experience. So then the cost would be, who's taking that, it's also called reply memory, and here basically the mean square, or the average of the cost along all the samples here. So basically we continue playing this game, storing memory, then taking the cost of this network by predicting the Q values of actions, the Q values of the actions with the next state, and then estimating the difference between them. And once we reach, for example, cost equal to 0, that means we are always predicting the correct Q values of our action. So the algorithm here is called the E-greedy Q learning. The E-greedy here basically use a trade-off between exploration and exploitation in reinforcement learning. The idea of exploration and exploitation is like what we did with the room game. At the beginning, we don't have any policy. The agent doesn't know anything about what to do. So at the beginning, the agent will start to do random actions, basically actions, yeah. And this the idea when the agent is doing random actions is the phase of exploration. So it's only exploring the actions and what reward it can get from this action. Then the exploitation is basically usually mixed between exploration and or randomness and actions that are taken from the network itself or from the Q matrix. And the idea of the actions that are taken from the Q matrix, that means we put the input on the network, we get the predicted Q values, and then we take the action that has the maximum value. So the E-greedy, which is basically here we have the epsilon there, and this epsilon basically is a kind of a probability of selecting a random action. So this epsilon usually starts very high, which means 90% of our actions will be taken randomly. This is where the exploration is done. Then, for example, after 100 iteration of the game, we actually exponentially we start to reduce this epsilon from 0.99, for example, to 0.01, where the action now are taken by the network most of the time. So at the beginning, 90% of the actions are randomly. At the end, only very few actions are taken randomly, and the rest are taken from the experience. So this is basically starting from the exploration. Complete exploration is into the complete exploitation. And the idea here that we now start with the episode of this game from 1 to m. We initialize a state, for example, from the first state. Then from t to t basically here to terminate basically with probability of epsilon, as I said, let's say at the beginning 90%, we select the action randomly. Otherwise, if we are now in the exploration, we select the action that has a maximum value predicted from the network. Then we execute that action because now we can, for example, move the agent down in the Pong game. And then we observe the reward of that action. And we observe also the next state, what happens. For example, when we move down, then we see the agent that is moved down. So we can, and also the ball is getting closer, so we can store that. So now we store this transition where we have st, action, reward, and the next state in D, which is here the memory, like we have seen here. This will be our memory. Then, for example, we need now to update the backpropagation. We sample random mini patch to apply stochastic gradient descent that contains some samples of this 4 combination from the memory. Then we need to basically estimate that cost and do the backpropagation with respect to that cost. Now, the only difference here that we see basically that we have y, just to understand if we are talking about the st plus 1, if the next state is a terminal state, which means the state when the game is ended, in the Bellman equation or in the cost function, we are using only the reward. But if the game is not ended, which means a non-terminal st plus 1, then we need to include the second part, which is this one. So only when I have terminates, I don't use this part. I only take the reward, the current reward. Otherwise, we use the that part. So this is basically our cost function here. So if it either could be just the absolute difference here, or it could be the, for example, like what we see there. So we have here this sum. Yeah, so I need to close it here and close it there, and it will be the mean squared error. Okay, because if you have negative values, they should be either mean squared error or absolute error, and this is what we see here. So this is the idea of deep Q learning. It's like the Q learning, but now we replace the metric with a neural network that estimates this metric, because when it comes to infinite states, then we cannot have a matrix. It's used very successfully in all games now. There's a paper that in the paper review list, which is about playing Atari with reinforcement learning, which is mainly about deep Q learning. So that's it for reinforcement learning, and that's it for our course. So I hope you enjoyed it. I hope you learned a lot of information, useful information from it. Reading the papers, also participating in the papers presentations also would be very useful for you. It will also enrich your information about deep learning. Thank you very much.